I am Maruti Mudunuru, and today I'll be talking about a physics-informed machine learning workflow for real-time unconventional reservoir management. And mainly the emphasis is on the demonstration of this workflow and a proof of concept at the MSEEL website, which is the Marcellus Shale Energy and Environmental Laboratory. I'll be discussing this in the next set of slides. And this is a big wide team effort from Los Alamos National Lab with collaboration with West Virginia University and NETL. And this is a part of the US Department of Fossil Energy Smart Initiative. And hope everyone can listen to me, right?
Yes.
Okay. So this is a presentation overview. And so first I'll give a brief introduction of this MSEEL website and the premise. Why do we need to develop this machine learning workflow, and what is our premise on this pressure management? And the proposed approach, I'll discuss in detail about the physics-informed machine learning, this machine learning workflow, and the corresponding underlying physics of gas production. And what are the challenges involved in this developing this workflow when we are using field data, lab scale data, and physics-based models. And then we'll show you some of the preliminary results from both the modeling side as well as the machine learning side, and make the conclusions and path forward. Going into the details, so what is this MSEEL site? So the MSEEL site is a site developed by Department of Energy and provides a wealth of data for understanding the behavior of gas production so that it can be transferred, whatever the knowledge that is gained from the site can be transferred to other sites where there is minimal data. So the left figure here shows the drilling of a science well, which was done in summer 2015. It's called a MIP3H well, and the bottom figure shows a diagram of different wells, different gas wells that were developed along with the science well. In the science well, we gather a lot of data from this science well, and the MSEEL's project objective is for understanding this unconventional oil and gas production, and is one of the DOE's field lab site. So what does this site give us? It gives us an opportunity to validate field strategies, develop and validate new knowledge and technology, which was not available previously before. And the goal is to enhance the recovery efficiency with minimal environmental implications. So all the data, the extensive data related to the MSEEL website, MSEEL site is posted on this mseel.org. So anyone can go and look into various types of data sets. For example, like gas production, daily gas production, what might be the possible water production from this site. And so this MSEEL site is currently producing gas and is developed in 2011. And after that, there are like 4 wells added to the system, and we have extensive data available both from the lab scale as well as the field scale data. So this includes the lab scale data, includes a core and other types of information on the fracture network, and the field scale data includes information on the gas, water production, and the distributed temperature sensing, which provides information on the production at each and every stage, and fracture mapping. So this site is located in the Morgantown, and the restricted production provides a good opportunity for future field tests. That is one of the things is the pressure management. So what is this pressure management and what is our premise? So our premise is mainly like machine learning when coupled with synthetic data can be used to inform decisions in real time, leading to an optimized production strategy. So the left set of figures show various papers wherein which we have strong anecdotal evidences from field experiences saying like pressure drastically affects various types of drawdown strategies and production from the shale gas formation. For example, what we see in the bottom right figure here is a cumulative production versus time. So if you have if you draw down very rapidly, that means you reduce the well pressure very low, then you have a really neat production. Like then you get a lot of production initially, but the decline in the production curve is very drastic after a certain time, and you may not be able to extract the entire hydrocarbon from the reservoir. But if you draw down the system slowly, that means if you have a higher well pressure, then initially you are producing less amount of oil, but on a long term, you are able to extract a higher amount of hydrocarbon. So there's a compromise between these two, and we want to give operators a production strategy based on this pressure management and machine learning for higher overall production. So there is like an unquantified benefit with this procedure. So now going into our overall arcing goal, like what is the basis for this research? So the goal is to develop a predictive basis for optimizing reservoir management at various shale gas sites through pressure management strategy. So as discussed before, what is a sweet spot? What is the main thing we are interested in is crossover. When does that occur in time? Does it occur like 5 years from now or 10 years from now? And what might be the drawdown strategies one should be interested in when you have this crossover, and what might be the operating strategies and fast simulation tools that can help to provide this drawdown strategy. So for that, so the premise is like we need to have some experimental data to say that if you draw down fast and draw down slow, how does the fracture behave? How does the underlying stage behaves? So this bottom curve shows information on how does the permeability change with different drawdown pressures. So as you can see in a lab scale setting, so as you increase the drawdown pressure, the aperture decreases. That means the fractures are closing, resulting in lesser and lesser production. So if you have fractures to be open, then you have a lot of production, but the fractures are closing due to higher pressure drawdown. That means those parts of the reservoir are not accessible. So that experimental data confirms our pressure management strategy to quantify this behavior. So now we have this experimental evidence for this permeability pressure relationship. How are we going to extend that to a field scale and validate our workflow and machine learning tools that can be applied to any site? So to do that, we have this proposed machine learning workflow. So this is an overview of the proposed machine learning workflow, wherein which we have only information at a given site. You only have information on the short-term production data. For instance, like the red curve given below, like you have information for like around between starting from 0 to 90 days, and you want to know how does the production decrease or how does the production rate change over in the span of an year or in the next set of couple of months. To do that, what are we trying to do? So given this short-term production data, define site-specific parameters, and from the refined site-specific parameters, we give it to ML predictors, that is the ML forward models, which provide information on long-term production prediction as well as the associated uncertainties. So this is the overall workflow. Now going into the nitty details, what are the various components of this workflow and how does the workflow construct these machine learning forward and inverse models? So the workflow utilizes a library of data on site-specific behavior to inform both the history matching and forecasting models. So the left side, so the top set of tools and the bottom set are the data sets. So given a range of possible site characteristics, so for instance, at the MSEEL site, given the information, the permeability, the porosity, the fracture network, and other types of physics information, our goal is to develop accurate physics. And this is achieved by data generation, resulting in a synthetic production data. So with this accurate physics and a range of possible site characteristics, we develop a site behavior library, which encompasses both the synthetic production data as well as the early production data. This site production library is like a library wherein which you can see how the production changes with different types of permeability scenarios, fracture spacing scenarios, as well as pressure management scenarios. And this site library is fed to an ML inverse model, and this ML inverse model is used to refine key site parameters for a given specific site, for example, like MSEEL. And then based on this key refined site specific parameters, we provide it to a forward model which provides fast and accurate physics, and even use strategy, we evaluate these quantities of interest, that is the total cumulative production, total gas production, stage specific production, and also the spatial amount of gas that is left over. So going into the specific aspects, so what might be the key mechanisms that need to be incorporated to develop this site behavior library? So for that, we need to account for mechanisms at various scales and with appropriate detail. So the simulations that provide the synthetic production data must accurately represent meaning of the fractures, as well as also how the fracture spacing happens, and also the proof of concept related to comprehensive and accurate simulations. Any questions so far? And okay, going forward, so this MSEEL provides a unique opportunity for proof of concept to test our pressure management scenario. That is, like, we have extensive data to allow for comprehensive treatment, and this also allows us to provide future validation sets. So now going into a site behavior library. So why do we need a site behavior library, and what are the parameters that need to be changed to produce this site behavior library? So we can have any simulation data, for instance, any simulators from oil and gas industry, or any DOE set of simulators that provide the synthetic production data. And any platform can be used to generate the synthetic data library. And the synthetic data provides insights on what might be the possible labels, that is, what might be the physical set of parameters or the features from the time series data, from the production curves, or associated underlying metadata like well logs or any other information from the drilling that helps us to constrain the poorly site parameters that are not available, and also understand the production scenario libraries that are not observed. So the site behavior library can be updated with field data as it becomes available, and you can also augment data from other sites. Now, on the history matching side, once you have this site behavior library, we are feeding that to a machine learning inverse model. This machine learning inverse model tries its best to calibrate for a forward model and refines the key site parameters. That is, like, we might not know what might be the set of parameters for a given set, but we know the mean and also the variance of the set of parameters. And once we have this range of parameters, we can know what might be the constraints on the key set of parameters and refine that. Once we have this refined set of parameters, a forward model can easily capture the reservoir behavior accurately and enhance this predictive capability. And for a given user drawdown strategy, like a given set of pressure strategies, then we can estimate the total amount of cumulative production, as well as the stage-specific production and how much amount of hydrocarbon was left in place. Now, how do we develop this library? How computationally intensive is to develop this library, and what are the strategies? So to explore and develop this library, we need to explore the entire parameter space, which might not be a physically realistic as the computation cost is very high. For example, like to generate expensive discrete fracture network simulation with full physics, it takes like a simulation run will take like around a day or so, and on a on a different set of grids, and that is not computationally tractable to develop the site scale library. So we only use expensive DFN runs, only a few of them, to generate a high fidelity library, and we use a reduced physics models, for instance, like any reduced order models that are available in literature for oil and gas, or graph-based models. This can include graph-based machine learning models that are pre-trained, and develop a scenario wherein which you have a reduced order physics which can provide a library for tens of thousands of runs. So once you have these two set of libraries, you can fine-tune the ML inverse model with transfer learning, for example. Like we can use like BERT or any other machine learning model that can inform both high fidelity and low fidelity libraries to combine this in a fashion such that it can provide training and also the final ML inverse model. So this inverse model provides information on critical site parameters to constrain physics-based models. So now going into the data. So how does the field scale data, how does the lab scale data look? So for the field scale data, so these set of figures show how is the real well scenario look like, and also the locations of perforations which are needed to develop a discrete fracture network model, and the fracture from the microseismic heights. We get information on the fracture length, and along the lateral we have different types of information. So this extensive data sets are used to develop a discrete fracture network model and used to upscale it to understand and develop the site scale behavior library. So how does the lab scale data inform the theoretical models? So lab scale data provides a plethora of information to inform theoretical models. For example, it can provide information on how does the fracture aperture change with effective confining stress. So how does the fracture aperture change when you have a higher confining stress compared to lower confining stress? As you can see here, if you have a higher confining stress that is like around 25 megapascal, the fracture aperture changes drastically, which is in the order of almost like 0.2 to 0.1. And this type of information can be used to inform theoretical models wherein which you have pressure permeability relationship based on Barton bands. And this can be used to inform theoretical reduced physics models to see and quickly understand how does the cumulative production change with time, and how does the production reflect transport of gas at different scales from nanoscale to field scale. How does the pore size change with the change in stress? What might be the effective distribution of the gas and other types of access to the reservoirs based on the pressure management scenario. So we have this information, and these information are fed to the reservoir scale models. So what does a reduced physics library look? How does a gas production library look based on reduced physics model? For the reduced physics model here, we show a model developed by Padzek, which is very famous in the oil and gas literature. And this Padzek model provides information on how does the gas production from shales look like, for example, the Barnett Shale. And it provides a simple model, which is a nonlinear pressure diffusion equation. And the nonlinear pressure diffusion equation is solved using a Newton-Raphson method with a scaling curve for transport of fractures. So it assumes like each fracture produces same amount of gas, and the entire production curve is sum of the productions from each and every stages multiplied by the stage factor. So this is how the model equation looks, which is a nonlinear pressure diffusion equation, and M is a pseudo pressure, and which is manipulated to get the amount of gas from the system. And the parameter which is important for this equation is the hydraulic diffusivity, which is the amount of gas that is the information from the permeability, porosity, and gas. production library. So for a high-fidelity library, we use a DOE simulator, a massively parallel multiphysics code called pflowtran, wherein which we develop this library to solve for both flow and gas, wherein which densities are accounted for the equation of state. And the flow is based on the mass conservation equation based on Darcy's equation, and the equation of state, which represents a density with respect to pressure, are given by different sets of scenarios. It can be a constant or an ideal gas or any information from the MSEEL website. And the transport, once you have the flow, you want to access which pockets of the reservoir are accessible and which pockets are not. And this gas transport equation, which is given by the advection diffusion equation, provides information on how gas transports from different pockets of the reservoir into the well. So these are the set of parameters we vary to develop our high-fidelity library. There are almost like 13 to 15 parameters, which include gas diffusivity, methane gas properties, and these are all the information we have from the MSEEL website and from the well data from the science well, the matrix permeability, tortuosity, fracture network properties. And the other things which we also have in high fidelity range is the well pressure and the pressure boundary conditions from the DTS data. And also what we are trying to account for is uncertainty in the hydrocarbon in place, that is which pockets of the reservoir have highest hydrocarbon compared to others. And this results in a different set of simulation parameters which we need to solve for. So going into the results, so how does a side scale library look, and how does the fracture network and associated stage look? So to develop this fracture network model, we have this stage. We have a horizontal well, wherein which you have three different hydraulic fractures and natural fractures which are intersecting these hydraulic fractures. These natural fractures are then upscaled to a continuum model using an octave refinement, and the upscale porosity and permeability provide information to the pflowtran simulator. So once we have this upscaled model, we perform a gas flow and gas transport simulation on the system. So to account for permeability with stress relationship, we have this Parton banded stress relationship. So when you have higher drawdown pressure, the fractures close and you have less gas transported into the well. So the initial testing, a preliminary set of results based on upscale model shows like characteristic behavior is tied to the hydraulic fractures. Here you can see this is a well and these are the hydraulic fractures. Initially when you have the entire hydrocarbon in place, as you can see, as the time progresses, the hydraulic fractures get activated and a lot of drainage is happening in this hydraulic set of fractures. Now, using this library, what we have done. So using this library, we have developed a simple deep learning model wherein which we train for all the set of parameters for history matching. And to train this model, we use PADSEC for different set of parameters and library scenarios, and this figure shows how does the prediction look like. So for the deep learning model, what we input is this red curve, which is a time series, which is the initial 90 days data, and we have two sets of parameters, non-dimensionalized, and these dotted lines provide production values at different scenarios. And we are able to mimic different set of scenarios based on this synthetic library. So now moving forward, like how does the system behave for different set of pressure scenarios? So for a pressure management scenarios, we want to explore for different types of pressures, wherein which you have pressures going from higher drawdowns to lower drawdowns. A simple scenario is like a sinusoidal curve, or accounting for different higher order terms. So this blue curve represents a pressure scenario which which is a sinusoidal curve, which has a mean around 12 and maximum around 17 megapascal. And this red curve shows a production response from the P-flow trans simulation. And as you can see, when you have a higher drawdown pressure, you have a lower production curve. And when you have a lower drawdown pressure, you have a higher production curve. And you can see similar set of characteristics and how does the higher order terms influence the pressure management strategy. Now we have this pressure management scenario, and we have this pressure inputs for the P-flow trans code. Now how does this model perform when you compare it for a field scenario? So this is the most important one, which is a comparison of gas production field scenario with P-flow trans simulation. So this blue curve is the real field data from the MSEEL website, and this given this pressure curve as an input for the P-flow trans simulation, what we have done is we have this red production rate curve, which is the output from the P-flow trans simulation, superimposed on this field production magenta curve that is obtained from the MSEEL website. As you can see, the P-flow trans, the synthetic P-flow trans simulation based on the realistic parameters from the MSEEL site shows promise when compared to the field scenario. It is able to qualitatively and considerably qualitatively able to predict different set of pressure profiles, as you can see from this curve. So this shows promise in developing a lesser number of high-fidelity simulations, which can be augmented to the low-fidelity simulations to develop a machine learning forward and inverse set of models. Now going forward, we have shown promise, like we have shown preliminary set of results and promise in this workflow applied for the MSEEL real data sets. And the next step is to enhance this data and provide pressure management strategies in ways in which we can improve the production overall for a longer period of term. So having said that, I'm happy to receive any questions. Thank you.
Thank you. Any question from audience?
I have a question.
Yes.
This is Panos. Okay, I can ask it actually on this slide. So is there a feedback mechanism somewhere here so that when you produce the new data that I can see, for example, here, do they get back into the site behavior library as part of the synthetic data?
Yeah, that's what we are doing. So for instance, this curve, for example, this one. So here we have used the data.
Which one do you mean?
So for instance, in this curve, so we have the pressure from 0 to 1,000 days, that is from 2011, sorry, from 2015 to the August of 2019.
Okay.
And we have developed this information on this production scenario. And for the active loop that you're talking about, that means like given a pressure scenario, how does the production look like? We have held this data set out to see how the system behaves, and that shows like a reasonable comparison between the synthetic data compared to the field production. So does that answer your question?
I think I asked something different. That when you produce, can you go to this slide? So you have the second box there where you compute fast and accurate physics based on the refined parameters, right? So then these give you these things in the boxes, the total cumulative production, etc., right? So these new values, do you actually store them back in your site behavior library so that you have a feedback loop that hopefully at some point going through this loop, these
Yes.
refined key site parameters will converge to their final values?
Yes, that's right.
Okay. All right. Okay, thank you.
We store those values and for developing the machine learning model.
Yes.
So what we do is we first only use the first 90 days. As the new
Yes.
site data becomes available, we
Right.
augment the site behavior library with this new set of data.
Okay, yes, that was my question. Okay, yes. So have you seen any kind of convergence of the with time of the refined parameters?
That one we are still working on it because we have only the new production data that is available right now.
Okay.
So we are still testing on that. So the answer to that question is we are still testing.
Okay. And in one of your first slides, in addition to the ML-based inverse model, you also had an ML-based forward model. Can you go further back? Further, more. There, this one. So here, you haven't implemented yet ML forward models, right?
Yes. Yeah, we don't have, like we are still in the testing phase. We did not show you the ML forward model.
Okay.
The ML forward model is just like, you have a set of input parameters, that is the 13 set of input parameters which represent a stage. And that given that set of parameters along with the time series here, how does the production curve look?
I see. But you're still testing that. You didn't show us any result of that.
Yeah, I did not show you any of those results.
Okay. All right, thank you.
So in your site parameters, are you updating the spatially varying parameters like permeability or other differential parameters? Or just estimating quantitative interest you are interested in, like production?
So updating the site parameters means like history matching, right? So the history matching is the ML inverse models. Yes, the answer to that question is yes. So we are updating the site specific parameters, but the curve here I've shown you was based, for instance, this one. Sorry, this one. The curve which I've shown you here are the mean set of parameters. So this like ML will be used to fine tune this to extract how does the spatial parameters change as the pressure changes. So like there's a permeability or porosity change over time when you have different pressure management strategies. That's what we are trying to do through that history matching. So I did not show you that one yet.
Okay, thank you. Any other questions?